So, hello, welcome everyone to our BOF about accelerating AI with open standards and ecosystem insights, which is held by the ML Council from Khronos. So, the outline for today's BOF is, first I'm going to talk about motivation and purpose of something we call the Khronos AI Ecosystem Research Project, where we wanted to understand where the AI ecosystem currently stands. We're going to explore the problem why the AI acceleration ecosystem is so complex, why it's so hard to get good acceleration across a wide set of accelerators. We try to get a technical understanding why performance portability is hard, and get finally to some solution exploration, how open standards can help and how Khronos might be able to help to simplify the life of developers. And in the end, we are going to have an open discussion where we welcome your thoughts and your feedback to give us more input about what you think would be good from us to provide to you. Okay, so let me first talk about Khronos ML Council Group activities. So we mostly arrived the ML Council Group half a year ago, and the goal is to discuss the current challenges in cross-platform ML development and deployment. Within Khronos, we want to ensure that knowledge of the machine learning domain gets transferred between all the working groups and all the partners so that they can make good, educated developments of the hardware and software APIs. We also want to get feedback from the industry about what you need in machine learning to have successful software deployed to any platform. And we're also providing feedback to any Khronos and API implementer who has interest in machine learning. And to begin, we started to conduct a market research to understand what's going on. And for the working groups themselves, we are working with really nearly all of the working groups who have some kind of overlap with machine learning. So the Vulkan group, OpenCL, OpenVX, Lang, SPIRV, SYCL, and NNEF, all of those groups have similar problems bringing machine learning to their APIs. So a pretty nice overview about the ecosystem is something like this, where we have open source frameworks, and the number of those frameworks is quite low, at least the one which are used frequently. And all of those frameworks use a set of compilers, runtimes, and or libraries. And this amount of libraries is already quite huge. Which of those frameworks is a good framework? If you would want to use PyTorch, you have to choose a backend. Which backend do you choose? Are those backends portable? You can be used by everyone. Are those specialized to just one certain NPU? And even for those backends, the question goes further. Which acceleration API is being used by the backend? If you're going to buy hardware, do you want to have good Vulkan, SYCL, OpenCL support? Do you use NVIDIA only and you don't care for those? Do you want to have DirectML because you are deploying on Windows and have a DirectX application? And there's a huge list of APIs which is missing over here. It's each and every NPU vendor has at least one API to access the NPU as well. We would need multiple slides over here to list all of those. The landscape is super complex, and we want to understand why it is so complex and what we can do. And also we want to understand how open interoperability standards can help. And in general, open cross-vendor APIs benefit both software and hardware vendors. If you're a software vendor and you would have an open standard which is implemented by multiple hardware vendors, it means for you, you have reduced costs in implementing your software for all of those vendors who support the standard, and you will also have a broader market reach, because every vendor implementing the API is a target for your software. And if a new vendor comes in and would implement the API, it will immediately become a target for your software. For hardware vendors, it's basically the same. If a hardware vendor comes and they have a proprietary API for their new machine learning chip, then the hardware vendor would have to work with the whole ecosystem to get this chip supported, with the whole ecosystem which is of interest. If they would implement an open standard, then it would get access to the whole ecosystem as well. But if we make an open standard, it has to be extremely robust because it has to be stable. And as many companies as possible should work developing the standard to ensure that we don't miss anything. And also we have to get a good timing for acceleration standards. If we are too early, then the whole space might move and the API might have to change too often. And if an API changes, I can imagine that a lot of you might not be happy if you have to change your code for every year for a new API version, which might break your code and not just add new features. At the same time, we want to be extensible always, so that if a vendor has a new idea and wants to expose it so that you can experiment with it, we want to be able to expose it inside this API so that you can play with it, and then we can find a consensus within Khronos to see how it will work for each and every IHV. So looking at the open standards activity within Khronos, we have NNEF, and currently there's NNEF 2.0 in work, and it's quite interesting because it's not defining operators anymore, but it's trying to define a tensor language, script-ND, to define custom operators, and then you can have a tensor library built out of those tensor shaders to build models, removing the need to discuss about what is a good operator set. We have Slang, which is presented as modern shading language and open source compiler, and it has all nice features like reflection specialization and auto differentiation, and it's a pretty good target, for example, for neural graphics. And I'm pretty sure it will be used more widely in the future with new features. We have SPV, which is our hardware agnostic GPU IR as compiler target, and this one it got a lot of extensions to map matrix operations or matrix vector operations to our two tensor cores, so that you get faster matrix multiplies. And completely new, ARM released their TOSA extension for Vulkan machine learning, so that you can have a complete machine learning graph within Vulkan with a fixed operator set in SPV and Vulkan. And finally, we have Vulkan and OpenCL, which are both cross-platform execution APIs, which give you all the low-level stuff you need for shared memory, synchronization, tiling. We have tensor intrinsics, cooperative matrices, but also new ML types like bfloat 16, FP8, and 8, so that a wide range of ML workloads can be executed on those compute APIs. Okay, looking at the ML adoption of Khronos standards in inference frameworks, OpenCL and Vulkan are the two most widely adopted ones. I don't want to talk about all of those projects by themselves, but it can be seen that Vulkan is getting traction now, while OpenCL has a lot of support from the beginning of OpenCL development, but also has support for quite new operations, new libraries like GGML. And so with all the information we decided, okay, we really want to understand the ecosystem. So we initiated the Khronos ML research project to understand which Khronos APIs are supported by how many ML frameworks, but also is the work we are currently doing within Khronos, for example, with the tensor cores for machine learning and the new data type, sufficient to provide effective acceleration in practice? Or what are emergent effective directions for ML acceleration stack? What do we have to do? And what can open standards do to provide a real ecosystem benefit and not just another operation which might help you for half a year? And the most important question we have is, can we finally crack functional and performance portability? Usually, frameworks currently solve only one of the two problems. We haven't seen anything which solves both. And we have to figure out if there's a way to get both working. And with all of those, Khronos has initiated our AI ecosystem research project to understand those market realities. And many thanks go to FutureWay, who sponsored this project. And now I pass over to Mr. ML Perf, David Kanter, who is responsible for the project itself.
Thank you so much for the introduction, and thank you all for joining. I just want to note there's a little bit of irony here, which is there's fewer people in the room for ML than graphics, which is, I'm never used to ML being the less popular option. So it's a little bit refreshing. Let's see. There we go. As Markus said, I'm David Kanter. I am one of the co-founders of the MLPerf project, and I was the founding executive director of ML Commons, and have done a lot of work in this space, including the patents for Cerebrus systems, and I've been working in computer architecture, graphics, and other places for about 16 years. I brought together to work on this project two of my friends and colleagues, Victor Bittorf, who was previously at Google Brain and at PyTorch, where he has extensive experience working on hardware-software co-design for AI, and Peter Glaskowski, who's been an industry analyst and system architect for many, many years, working at Microsoft, Intel, and more recently Esperanto Systems, which was an AI system and processor startup. Broadly speaking, the goal of this project is to understand the ecosystem for ML acceleration and what standards bodies, in particular the Khronos group, can do to make that acceleration more pervasive so that we can bring the magic of AI into the hands of more folks. Broadly speaking, how can we make AI much cheaper, easier to use so that it becomes a more powerful force for good in society? So let's first dive into the problem. As we started exploring the problem, we set out sort of a menu of who we wished to speak with, and that's up on screen right now. We wanted to talk to folks at sort of every stage of the stack, from the silicon up to developing and deploying models and everything in between. And we wanted to explore what are the top problems that people are facing through the format of one-on-one interviews. Generally, our finding is that the biggest problem is doing anything with AI requires expert work and far too much of it. The vast majority of our respondents indicated this. And so on one hand, this is great, because as you all know from optimizing code, if you have one problem that everyone agrees on, that's a lot better than having 10,000 problems and death by a million paper cuts. So we have one big problem to focus on, which is great. Generally speaking, what we found is that when it comes to portability and performance, everyone falls into one of three buckets here. There's the situation of one-to-one, where you have one model that you're optimizing for one device. One way to think about this is potentially the early days of Tesla, or the camera app inside many smartphones. You know the platform, you know the model, you may control both, you can optimize it quite extensively. However, any degree of success in this scenario will quickly get you into either the one-to-many or the many-to-one, which is to say that you are going to rev your platform, right? If we, again, take the example of Tesla, there are several generations of their drive accelerator in the cars. Sometimes you're lucky and they're simply different versions of platforms that you control, but as the picture indicates, it might be something much more akin to you need to run on both a workstation and a smartphone with a single network. Conversely, at the bottom, you might, as a device manufacturer or a platform vendor, be worried about how do I get multiple networks to run on my platform? How do I get them all to run well? Right? That is the problem that an NVIDIA or a Qualcomm faces, whereas the one-to-many is more commonly you're an application vendor. So great, these are all problems. You can solve them with experts, but we just don't have enough experts, and that's really the core issue here. One of the questions we asked is, should we be looking at training or inference, or maybe both? And the answer here was a pretty resounding emphasis on inference. And the reasoning is up on this slide. At a high level, I'd say that training is, while being more performance demanding on sort of a per job basis, it's actually less performance sensitive because the acceleration that you may get is oftentimes not qualitatively different. Qualitatively different, right? The difference between this job runs in a cup of coffee, this job runs in a millisecond, and this job runs in a day is huge, but this job takes 2 months versus 2.2 months is not very significant. Also, training is fundamentally about experimentation, which means it's hard to standardize, it moves very fast, and a lot of training is done on extremely custom systems. So it's just not a good impedance match for standards. On the other hand, inference is the much larger market, right? And if you think about this, if we were to use the metaphor of compilation, training is like compiling code, inference is like running it. And yes, if you were to think about Microsoft Office or the latest video game, you spend a lot of time optimizing the compilation, but the runtime is where it's all at, and that is inference. Additionally, inference is just vastly more diverse on almost every single dimension in terms of software stacks, hardware, power levels, and system scales. And so the value of standardization is greater there. One of the things that we kept on coming across is speed of light. And specifically, how do we get the speed of light? And Markus alluded to this earlier in talking about performance portability. So I wanted to throw up a definition here to help guide the rest of the discussion, which is, my definition here is speed of light is the best that you can do for a given model on a given system. So one way to think about this is, what is the performance you can get out of a model on, say, an Intel platform if you have a team of Intel engineers working on that and they have access to all the documentation of all the operations and cache line sizing and the greatest possible optimization that you can. And so one of the things that we found that is interesting is that ultimately actually speed of light is quite present for almost all inference. Many of the people we talked to called this out explicitly, but even the people who didn't call it out explicitly we're indirectly talking about the speed of light, and this is really important. So the business of the speed of light is really, there's a cost driver, right, which is that if you can improve performance and use less expensive hardware, you can deploy across a broader set of players, right? If you can take your application and instead of running it on a server, get it on a smartphone, your TAM is bigger, your product managers are happy, and so is your GM, right? The other aspect that you'll see is there might be straightforward competitive pressure, right? I have platform X, I want platform X to be as capable as platform Y, right? You see that in smartphones and PCs. But then there's also the, hey, I have a new feature that I want to deploy, and that has a performance cost, right? And so anytime you improve performance, ultimately that tends to drive the capability of new features and higher accuracy. Right, so speed of light is actually really important from a business consideration, which is great. So how do we get to the speed of light? And what does it mean to be close to the speed of light? What do you really need to get there? And as we were discussing with people, what we found is this spectrum up here. There are a lot of folks for whom, even 50% is good enough, but that is really people who are focused on prototyping or scenarios where portability is P0, right? You're not really focusing on performance here. Then you have this sort of 50 to 80% zone. And to be honest, very few people said that 50 to 80% of the speed of light was acceptable. This is sort of, maybe you might call this the valley of death. The most common case where we saw this happening was where people said that time to market was a first priority. But realistically, this is kind of a bimodal distribution where, and really the biggest mode is 80% or so. And that was the threshold that most people cited as acceptable. They're willing to give up 20% of the speed of light in order to get something that's more usable. There are a lot of folks who said, 80 to 95% is their target. And then there were a small number of people who said that greater than 95% is actually what they want. Although usually this was phrased in the form of, are you kidding me? I've got a team of 40 engineers and they'll kill for a percentage point of performance. Without loss of generality, you can think about this as someone maybe working on recommenders at a large internet scale company or some other situation where you're truly driving the bottom line. But 80 to 95% is really the percentage of speed of light that most people are going to want. And that's good. That sets our goalpost. That gives us some context to think about. So hitting the speed of light or close to it is pretty tough, and I wanted to call out some of the reasons why here. First of all, when you're talking about AI, typically there's pre and post processing. We'll talk about this in a little bit more detail later, but if you work with computer vision, it's very common to do image resizing and other scaling things, and that actually takes execution time. Second, data movement, especially with the advent of tensor cores and other matrix multiplication acceleration, data movement is a very significant factor, especially once you start talking about accessing network or memory. Different architectures will want graphs expressed in different ways. You may need to think about expressing a given mathematical operation in different ways for different platforms, and that can be complicated. And then one of the things we'll talk about a bit more later is custom operators. In AI, it's very common to see specialized logical functions that have been developed either to optimize for a given platform. Hey, my platform has cool, shift to the left, take the inverse hypercube or whatever. This is, I think, the example I've seen from some of my colleagues. And in this one case, this is going to give us great performance, right? Another very common aspect is that as you're deploying or developing a new neural network, you will need some logic that wasn't there before, that didn't exist in the ecosystem. And this is actually pretty common. And then the last aspect is quality. Ultimately, like computer graphics, AI performance can trade off quality, right? In computer graphics, there's many optimizations you can do that are not perceptually detectable. In AI, that is also true, right? You can oftentimes do optimizations like reduced precision without impacting accuracy. However, when you start doing that, you need to be very cognizant of that accuracy, because if you degrade the accuracy, that may not be acceptable. So kind of looking back at the last few slides and generally our interviews, one of the things that we found is that really the problem isn't just how do we get rid of expert work, but it's actually best stated as it is up on the screen, which is how can we achieve portability for AI models given the desire for speed of light without demanding a lot of expert work? So this is a hard problem, which is good. You don't want to be working on easy problems. And so now I'm going to dive in and talk about why it is that performance portability is so hard. And so first we're going to talk about what that might mean. So let's start with the example of a very simple model, something like YOLO, common in computer vision. Imagine we're training it on one system, a workstation, and now we're going to run it on a different one. Generally, you can sort of simplify something like YOLO as a pile of convolutions followed by rectified linear units. That's the activation function. So let's just take this sort of platonic, I won't say ideal, but simplification, and say we've got an Onyx graph, which is convolution followed by ReLU. And that's just what we're going to look at. Well, okay. That's the mathematical operations we're going to perform. We all know what convolutions are, but how do you actually express that? And you've got a bunch of different options here. If you have a platform that's really optimized for this, you might actually have a fused convolution ReLU operator. So one operator does it all, super efficient, great. On the other end of the spectrum, you might have to express this using a gem, where you need to think about reshaping and unrolling, and there's all sorts of things in between, right? And so at the end of the day, figuring out how that convolution and that ReLU is expressed for the system is the job of an expert human or compiler, right? How do you pick between these things, which is going to have the best performance? So next, I promised we'd dive in a little bit more on custom operators. So on new models, I think last week we saw the open source GPT-5 come out, right? So let's take that as an example. Something like 20 to 30% of the operators inside these networks are custom. And what that means is they're not supported in PyTorch or TensorFlow or any other framework. No one's really seen them before except for the creators of the model and the people they're talking to. And that means it's definitely not supported in your compiler, it's definitely not supported in your tool chain, and those are generated from an R&D team somewhere. And that means you've got to manually implement them. So likelihood of hardware support is basically nil, and it can actually take quite a while for this sort of support to come in through the ecosystem, even forgetting about, hey, let's change the hardware. But I mean, even to get it into the compiler can take a while. So we have seen things like Triton. Triton is a library from an OpenAI that is used to write operators swiftly. Operator performance isn't going to be portable. You get functional portability, right? You might have an operator that in fact runs on multiple different GPU architectures. But even there, GPUs are relatively similar. They may not run very well or at all on a TPU. And certainly the performance will not be great. There's a lot in here where the performance is a function of the geometry of the underlying accelerator, things like register file sizes, banking arrangements, caches, etc. As we look at the assignment and scheduling of operators, again, this is where humans and experts play a role. One of the challenges is as you're starting to map these operations onto a hardware platform, not only do you need that expert human, but you really need a detailed knowledge of everything in that platform, right? So if you were to take something like a smartphone, you can actually look at two SoCs that they have almost all the same IP blocks, but for instance, the interconnect network between them is different. And that will lead to an entirely different set of optimizations. Right? And so given all of that, it's a really tough situation to do this kind of optimization. Because ultimately, at the end of the day, that sort of expert knowledge really is only in the hands of whoever is providing the platform, both software and hardware. Right? It's not reasonable to expect, without loss of generality, Adobe to have experts on every single hardware platform out there, or the folks at ByteDance who work on TikTok, right? And so that makes this all very, very difficult because you end up with so many special cases. So I said I'd talk a little bit more about pre and post processing. I just wanted to kind of set the context here and the overall flow, which is typically what you'll see is you get some sort of input, you'll do some pre-processing, and I have some examples up here, right? For natural language processing, like with all of today's LLMs or image generators, you might do tokenization. A lot of image processing, I mentioned before, you might be doing resizing or normalization. And then there's often a batch of platform-specific operations you might be doing, like transposition or numerical conversion as well. Once you've done your pre-processing, you get to do your inference, and then you have your post-processing and then your final output. So the key points here are, first of all, you have both model and platform-specific pre- and post-processing, and there are some libraries that will help us handle that. OpenCV is a great example for vision, but the reality is there's so many different kinds of data out there, so many different kinds of models, you're not going to be able to capture this all. So this is a real challenge because ultimately a lot of this pre and post processing falls back to the host processor, and so if we can accelerate that, that's fantastic. Of course, this is also hard, so don't claim we'll be able to solve this on day one. And then last, to highlight the point of quality, how many of you here got to play around with image generators in the early days? Show of hands. How many of you remember things like this where you'd have like 5-thumbed dolphins or whatever, right? Like, this is just really pointing out, this is why quality matters, right? And one of the points I want to make here, and this is very much coming from an ML perspective, is quality sounds easy, but it is super, 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 super hard. It is an incredibly expensive problem. Developing the eval sets for this is extraordinarily difficult. And so as we go forward to say, hey, how do we accelerate things? We don't want to make life more difficult for developers who are doing the evaluations and need that correctness to deploy into the market. Some other points that came out through our conversations that I just wanted to share as kind of guidelines to think about, maybe lessons from the last 30 years. First of all, AI moves super quickly. It feels like every 2 weeks everyone's talking about a new model, right? That is a really difficult velocity to deal with, especially considering my prior point about 20 to 30% of those new models come with our custom operators. That's a lot of custom operators on an annual basis, right? So that means that whatever we do, we need to adapt very quickly. And that's really tough in the standards world, right? Standards and fast moving are not necessarily a naturally aligned set of keywords, right? So this is an intrinsically difficult problem. One of the other things that was mentioned is that while you can have a really large operator set, at the end of the day, getting support for it is tough. Like PyTorch is a massive library. There's tons of operators. A lot of them aren't supported, right? Having non-supported operators is not super helpful because people will start using them and then they've put themselves into the slow path. One of the consequences of that is sort of the bottom 2 points, which is if you have a union functionality of many technologies, right? This is the classic, allow the committee to design a camel. It's not very good. There's a lot of slow paths. It ends up too broad, and many people said that they had specific examples of things where this just did not work. And so one of the things that was called for is to say, hey, be clear and opinionated. Don't give us N+1 standards, as the classic XKCD cartoon says. That isn't helpful. What is helpful is, especially when we're talking about acceleration, like pick out the things that work and focus in on them, right? So we need to reduce the amount of confusion, focus people's attention in the right area. And that's really what will help us move forward. So now I get to turn it back to Markus, who's going to talk about some of the potential solutions we're thinking of.
Thank you, David. So everyone who spent time in implementing MLOps most likely went to either CPU or compute shaders. And for Khronos, compute is quite widely supported. We have Vulkan, OpenCL, Sickle, even OpenGL compute if you're interested in. And Vulkan itself is also quite widely supported now by GGML, TVM, Ivory, ExecuTorch. So if you go to compute, if you want to do it on your own, you have multiple choices. A lot of frameworks are already supporting compute, and within Vulkan, we added also a series of extensions to implement machine learning operations which require matrix multiplies, like cooperative matrix 2, which has more features, more use cases to be accelerated. We have an integer dot product and cooperative vectors for matrix vector multiplies accelerated as well. And also Vulkan added a variety of data types like float 16, int 8 mass, bfloat 16, and fp8 as well now, to have all the data types you might need in your modern ML application. But if you have compute shaders, you need experts. And those experts might have to do a lot of work depending on how close you want to get the speed of light on all the platforms you are interested in. Imagine you have M different frameworks. Yeah, each of your ML operations must be supported. And now imagine you have a large operator set for M. Then you have N different hardware platforms, and the hardware platform might not be just different vendors, even different chips by the same vendors. And yeah, you want to optimize those. So yeah, you have a lot of work already. But now, each and every IHV-K will release one or more platforms each and every year. And now you're in an optimization loop, where every year you would have to optimize m times n times k permutations of the same operation again and again and again. Imagine how much time you would be spending to get the speed of light. Hopefully some of those platforms can be combined and have similar performance characteristics, but there's no guarantee. So in the long run, compute shaders might not be the best target for performance portable machine learning. Just to give you some example why implementing something simple as a generic matrix multiply is hard. The operation is super simple. You have in the output C at position AY, you're creating a dot product of the mth row of A and the kth column of B, and that's it. And well, you're doing m times n times k multiplies and adds, and you're good to go. But then, if you're looking at the memory operations, in the best case, you have m times k plus n times k reads and m times n writes. This seems reasonable. You read everything once and write C, every element once. But in the worst case, you have m times k reads and m times n writes. So it's a magnitude more reads and writes, meaning your performance will be a magnitude slower potentially. And you have to optimize your gem for memory access patterns so that it's efficient. So we get to a memory hierarchy. And the problem with memory hierarchies, depending on which GPU or even CPU architecture you are, they're different. So you might start with a NUMA system, so multiple chips on one board. Then you have connected through some slow interconnect. Then you get your normal RAM. Then you might have an L3 or not, which you don't know, which is usually huge. You have an L2, L1. Then at some point you are getting to your register file, and well, the register file might have a few scalars or vectors only, but it might also have a few thousand registers. So your implementation strategy, where to keep data, changes a lot depending on the register file. And then you have GPU or NPU cores behind, which might have internal memory as well to keep data from registers cached for matrix operations. And yeah, if you're going from left to right, on the left side, accessing those memory regions are fast, on the right side, super slow. And especially between L1 and L3 or memory, you also have transaction sizes. Quite often it's between 22 and 128 bytes. And the goal is to minimize the number of transactions and to maximize the usage of the transaction data you did. If you are going to read 1 byte from RAM, it always means you are doing one transaction from RAM to L2, to L3, to L2, to L1, and from L1, the single byte is read to the register file. If you would have a quite small transaction size of 32 bytes only, it means you have only 3.125% efficiency if you wouldn't be able to use all the data you read to L1 before it gets trashed by something else. So if you have a bad memory access pattern and you just have collisions in L1, you trash the L1 always and you read always from RAM, and then your performance tanks to 132 of what you could achieve. It's really hard to get to something which works everywhere because you have to decide about all loop unrollings and everything to get to a good solution. Also, the matrix memory layout is quite important. I talked about, okay, you have a dot product between rows of A and columns of B. And, well, how do you store the matrix A and B? Usually, if you're reading data within a single thread or in a subgroup, you want to read contiguous data. If you would have row major data for B, meaning all the elements in the same row would be stored contiguous, then your implementation requires you to read contiguous columns of B within a single subgroup. But if the data would be stored in column major, you would want to do vector-wise reads. And if you have some special block layout, which is possible as well for certain architectures, then you have to think about, okay, how do I ensure that I read those blocks as efficient as possible, and you don't know the layout, potentially. How do you want to optimize for this one? How to get the number of memory transactions down. I don't see a good way. If you have a good way to make this solved in compute, tell me, and I will forward it to the working groups. And besides just memory, there are also other implementation strategy like, do you want to minimize power usage or do you want to maximize performance? Sometimes you might want to do more work to ensure that or more work which is duplicated so that you can do more work which is not duplicated in parallel. You want to think about how to efficiently assign and schedule the work across multiple cores. The more cores you use, the more redundant work you are doing, the more power you might need, but the faster you are ready for low latency. But if you have something which should run in the background and you want to have only 60 Hertz, but your network would run at 1000 Hertz, you want to minimize power, so you would want to run just on a subset of the GPU. And things get even more complex if you have heterogeneous platforms like a GPU and an NPU in the same system, and you might want to change dynamically depending on if your device is plugged in or not. And imagine you would have to write compute shaders for each and every use case, for each and every platform. It's hard. So the next question which usually will come up is, okay, can we do something like a meta command like machine learning operation hell, where we just expose ML ops, but each ML operation by itself is being passed to the driver. There is no information about which ML operation depends on which other one with regards to data. And well, it's already a big win because the hardware abstraction layer, meaning the driver, knows the platform. And if you just look at the gem, you can have a pretty good implementation. And if a new platform comes out, you get a new driver and you get a faster gem. But since each operation is independent by itself, you have to define the input and the output to this operation. And so you have to specify what's the layout. And then you might not have the optimal layout for the hardware to run the best implementation you can imagine. Also, if you have just two operations like a gem and then an activation function like a ReLU, you want to fuse both operations. You do not want to write the result of the gem to memory because it's a single operation and then have the activation function read the memory back. Then you waste a lot of bandwidth and limited the speed of the activation function to the speed of memory and not to the speed of your chip. So meta commands API don't work. So they have a use, but in general they don't get us to the goal we are interested in. So the next step would be a graph hardware abstraction layer. So we want to pass a full graph to the driver, including all connectivity information like which tensor is being sent to which other ML operation. And we let the driver, or the hardware abstraction layer, handle all the intermediates you can imagine. So this means the gem itself sends something to the activation function, and those two operations can be fused, and then we don't have to write the data back. If there would be a gem followed by another gem, we could write the output of the first gem in a way that it is optimal for the second one. So the memory layouts are controlled by the driver and or compiler to ensure that the memory layout is optimal and we can achieve the best possible performance. And if some new hardware decides to have a new memory layout, it's not the responsibility of the developer to understand it, it's responsibility of the driver to do it. But still, there's one problem with having a graph hardware abstraction layer. We have to define all the operators the graph can support. And yeah, David already talked about it. If you have a way too huge operator set, if you have any new IHV who wants to implement the API, it will be a lot of work. The operations themselves might change over time because machine learning operators, we get new ones every week or every month quite often, and then older ones might vanish. But once we added something to a driver or to the specification, it's really hard to remove it afterwards. So we would be quite careful, and it would take years for an operation to be integrated. And at the time we integrate the operation, it would already be redundant because something new came out. So a GraphL is the best option, but still has a lot of problems. And so comparing the GraphL and the computer, the feature sets we have, or the positive and negative aspects, are disjunct, mostly, depending on how you stretch the definitions. But on the computer, usually you need a lot of expertise. Performance is potentially not portable and not future-proof because you don't know future hardware. And if future hardware changes, you might not have access to the extensions at the time you're writing your application. NPU support, unless you have a fully programmable MPU, you don't have support for the MPU. And if you have Fusion, and you have new operators, you would have to implement all the Fusions or have a compiler which does everything for you. While on the GraphL, well, you don't need that much expertise because an ML developer knows all the ops and can just use them. And assuming the driver is doing a good job, you would have a portable, future-proof implementation. NPU support is available as long as the NPU supports all the operators we define in the graph. And if anything has to be optimized or if new operations come and we want to fuse, it's not your problem, it would be the problem of the driver. And there's a compiler which can handle all the different use cases for you. So, completely different aspects. And for the performance itself, on computer, we have predictable performance on Vulkan because you're optimizing for your platform, and you know your platform, and you know exactly what stuff is doing in Vulkan. So you know how fast everything will be, while in a GraphL, you have a compiler, and a new driver might tweak things, and then performance might change. So this is a slight disadvantage of a HAL if you're unlucky. And for the custom operator set, a computer, yeah, you have a new custom operator, you implement it, you have it. On a GraphL, unless you have a way to define custom operators, you cannot get a new custom operator unless you can build it from the base operator set, which is already provided. And so the question which came up in the ML Council after having all those interviews in the industry and also thinking about all the problems we have internally and you might have is, we have two things. If we could join all the positive features, we could have an API which might actually work. And this is the first vision which has to be worked out furthermore, but I want to present it to get feedback from you all to know what do you think. First of all, we would have to define a graph language, which would be a tensor shader language, which is completely independent of any hardware-specific details. Currently, there's NNEF 2.0 in development, which is open source. You can have a look at the specification already. There's a link on the lower right, which seems to achieve this goal, to specify how a tensor operation can be defined without defining anything about warp sizes, the number of SMs, memory layouts, whatever. Everything is completely transparent and has to be passed to a compiler. If we have such a tensor shader language, we could build up a library of tensor ops, but we wouldn't have to do the discussion within the working groups about what is the best library of tensor operations, because each tensor operation is built of primitives. And if a new tensor operator has to be introduced, we would write the implementation with the tensor shader and it is there. If a driver would support this tensor shader language, which would be compiled to SPIR-V, supporting the same features, then we would have a path for each and every compute-capable device and a certain amount of NPUs as well, if they're programmable, to support those tensor shaders, and so the whole tensor op library we would be defining. And basically, the tensor shaders would be the fallback for the platform for any operations a driver wouldn't want to support, or cannot support, or doesn't know about yet. So if someone comes to us and say, oh, I have flash attention 10, yeah, then they could define flash attention 10 inside tensor shader and pass it to something we call the SPIR-VML runtime, which is a construct we just invented, which would be an open source project. And the SPIR-VML runtime, the idea is that this one could query the driver, do you support this new SPIR-VML extension? And if the driver says no, we would have a compiler taking the tensor shaders by themselves, compile them to SPIR-V compute. SPIR-V compute is supported everywhere on OpenCL and Vulkan, and SYCL, hopefully. And then we can pass this to the hardware driver, and we are good to go. So we have a fallback which would run everywhere. But if the driver says, yeah, I support SPIR-V ML, then we could say, okay, for each tensor operation, we can ask the driver, do you support it? Or we pass the tensor operation library to the driver and the tensor ops, the whole graph. And then one of those two sides could decide, okay, those operations I know, I have an optimized implementation for the gem, for the convolution, for the flash attention, and for all the ops the driver doesn't know about yet, we would have always a fallback. We could go to compute, and we wouldn't have the problem that a new operation will take years to be available inside the driver. And the hope is that this way we will allow the ML ecosystem to evolve way faster, defining those ops with performance a compiler can deliver. All of you might be aware that compilers might not always achieve the same performance as the expert, but if a compiler could get to 80%, I guess everyone would be happy, and then we can still run optimization for everything else. And since the compiler would be part of an open source project, if someone finds bugs, yeah, you're free to fix them and optimize the driver. And yeah, with this, there are further questions coming to us. Like, if we have a compiler, can we use AI to drive the performance optimizations within this framework? We know that we have all of these different hardware characteristics, like number of registers, L1, L2, bandwidth, whatever. Can we have some generic framework which could use AI or some search algorithm to find the best possible performance on a system so that we don't have to tweak the compiler for each new platform? And to get to something like that, would it be necessary that drivers within Khronos would have to expose metadata which can be used by the compiler? Like, okay, I am best at a certain grid size, I have a certain amount of tensor cores, I have shared memory size. Can we give the information a compiler requires to the compiler in a portable manner, which can be generically used or not? We don't know, but we will explore. And with this, I would like to thank you. Say, please get involved. We have a survey. There's a QR code. Please scan it. In this survey, there's a question like, do you want to take a one-on-one interview with David's team? If you want to give David feedback about your thoughts, what you need, what's going wrong, what's going great, please say yes, give him your email address, and then he will talk to you. And this is your chance to influence machine learning within Khronos. And do we have time for questions? One question. And then I will be outside if you have more questions.
Just one last comment. So in particular, we'd love to get input from application developers. As you all know, the Khronos group is platform vendors. And so we really, really want to hear from developers who are deploying or developing ML about what we can do here. So please don't be shy. Find us afterwards. All right. Questions?
Thank you for the talk. I have a question regarding the workflow, what it could look like. So imagine you implement your network with the tensor shader language, But you also mentioned you're focusing on the inference, not on the training yet. So would you be able to train that now, or like how would you need to replicate that with PyTorch, train PyTorch and somehow load the weights over and then use that?
Okay. So, but in PyTorch you have an operator set, and in theory you could define the PyTorch operator set with a tensor shading language and import the same shader. So you would need tooling to get your workload integrated into this framework.
So you could use the shaders in PyTorch?
In PyTorch. If you would add PyTorch support for this framework, yes.
Just to set some context, I would think of this as, this is a vision for something that could be a backend for PyTorch, right? And so, if it's widely adopted, then, we might see some coordination or partnership on the PyTorch side to ensure that some of the things that are exposed that come to fruition through this framework could be propagated upwards, right? So if we see, let me give you an example of a custom operator. So suppose it's a custom operator that comes from many platform vendors. Everyone discovers that the, shift 3 bits to the left operator is really, really valuable, and that you might have upwards propagation into PyTorch, right? There's the other path where you might have a custom operator that comes in through the ML developers and propagates downward. Does that answer the question?
Yeah, it helps. I might come back to you, but I don't want to keep up the progress. Thank you.
Sure. Okay. Thank you for the question.